You hear about interstellar visitors, mysterious objects from distant star systems blazing through our cosmic neighborhood. First came Oumuamua in 2017, then Borisov in 2019, both strange, both unprecedented, but neither prepared us for what happened on July 1st. 2025, when the Atlas Survey Telescope in Chile locked onto something that would shatter every assumption about how matter behaves in the universe. This visitor carries signatures so alien, so fundamentally different from anything we know, that its very light reveals conditions that simply do not exist in our solar system. What does 3I Atlas tell us about worlds we have never seen? What happens when you measure the polarization curve of an object that defies every known category? And why are some of the world's top astrophysicists calling this the most anomalous celestial body ever recorded? 3I Atlas, the third confirmed interstellar object, racing toward the sun at 58 kilometers per second with an orbital eccentricity of 6.141, the most hyperbolic trajectory ever measured. But speed and trajectory were just the opening act. The real revelation came when scientists pointed polarimetric instruments at this cosmic wanderer and discovered something that had never been seen before in the entire catalog of solar system objects. If you value documented astronomical discoveries like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. Also, this script is researched and factual, using sources from the archive preprint server paper 2509.05181 ICE, published September 5th. 2025 by Zuri Gray and 15 co-authors from institutions including the European Southern Observatory, and Avi Loeb's analysis published in Medium on September 10th, 2025, based on Harvard-Smithsonian Center for Astrophysics Research. These sources represent cutting-edge, peer-reviewed astronomical research that most people never see. Now back to the information. Light carries secrets. When sunlight bounces off an object in space, the way that light vibrates, its polarization, reveals hidden details about what it hit. Dust grains, ice crystals, surface composition. Every asteroid and comet in our solar system follows predictable polarization patterns. Negative polarization at small viewing angles, flipping to positive around 25 to 30 degrees. The physics is solid. The measurements are consistent. Until July 17th, 2025, Zuri Gray and her international team turned 3 of the world's most powerful telescopes toward 3I Atlas. FORCE 2 at the European Southern Observatory's Very Large Telescope in Chile. ALFOSC at the Nordic Optical Telescope in Spain. FORIRO 2 at the Bulgarian National Astronomical Observatory. 18 separate observations over 6 weeks. Phase angles from 7.7 to 22.4 degrees. What they found broke every rule. Negative 2.7% polarization at phase angle 7 degrees. No solar system object has ever recorded anything close to this depth of negative polarization. Comets typically show shallow negative values, maybe 0.5%. Asteroids rarely exceed 1% negative. But 3I Atlas hit negative 2.77% at 6.41 degrees according to Avi Loeb's September analysis. That's 5 times deeper than normal comets. The inversion angle, where polarization flips from negative to positive, occurred at just 17 degrees. Solar system comets flip around 25 to 30 degrees. The combination of extreme depth and low inversion angle has never been recorded, not once. In the entire database of comet polarimetry maintained by Nikolai Kizelev, covering decades of observations from observatories worldwide, nothing even approaches these numbers, but the measurements held, 3 different instruments, multiple observation nights. Statistical significance beyond question. The team used aperture polarimetry with roughly 2,000 kilometer radius to avoid contamination from background stars. Each measurement confirmed the anomaly. This was real. Avi Loeb, former chair of Harvard's astronomy department and head of the Galileo project, called it unprecedented among comets and asteroids. The paper, submitted to Astrophysical Journal Letters, established 3I Atlas as uniquely distinct in polarization properties from all known solar system bodies and even the previous interstellar comet 2, I Borisov. What causes such extreme negative polarization? The answer points to dust, unlike anything in our cosmic neighborhood. Polarization depends on how light scatters off particles. Size matters, shape matters, composition matters most of all. Solar system dust grains formed from materials available during our sun's birth 4.6 billion years ago. Silicon, oxygen, iron, magnesium, the usual suspects. But 3I Atlas carries dust signatures, suggesting formation conditions absent from our solar system. The extreme negative polarization resembles certain trans-Neptunian objects, Huya, Ixion, Varuna, and the Centaur Pholus. These distant and icy bodies show steep polarization curves at small phase angles, but they are solid objects with consolidated surfaces. 3. Atlas is an active comet with a diffuse coma of gas and dust. The comparison points to ice-rich particles with unusual optical properties. Light scattering models by Olga Ivanova and colleagues in 2023 showed that reproducing deep polarization minima requires highly porous ice particles. Their simulations treated grains as aggregates of sub-micron building blocks with silicate organic cores and water carbon dioxide ice mantles. Particle size and porosity shape polarization curves. Larger, more porous particles shift the negative branch deeper and narrower. 3. Atlas appears red in color, redder than the solar system comets and D-type asteroids. Multiple spectroscopic studies from Cyril Opitom, Bryce Boline, and Carlos de la Fuente Marcos confirmed the reddish hue through August 2025. Red surfaces typically contain organic compounds, complex carbon-based molecules that form under specific temperature and radiation conditions. The dust around 3 Oitinano. Atlas likely contains layered structures or fine textures shaped in an environment far removed from our own. Conditions that produced grain sizes, porosity levels, and compositions never seen in solar system materials. Water ice detection came on July 20th, 2025, from Gemini South and NASA Infrared Telescope Facility observations. Swift Observatory found water vapor and hydroxide ions on July 30th and August 1st. Spherix mission. Caltech reported bright carbon dioxide emissions on August 21st. Very Large Telescope confirmed cyanide and detected nickel vapor on August 21st. But the polarization remained the defining anomaly, the signature that screamed alien origin. Subscribe. If discoveries like this fascinate you, breakthroughs that rewrite textbooks happen rarely. Comment your location so we know where science curiosity lives. This research comes from institutions like the European Southern Observatory and Harvard Smithsonian Center for Astrophysics, representing the absolute frontier of what we know about interstellar objects. Now back to what the polarization reveals. The Hubble Space Telescope captured 3 Atlas on July 21st, 2025, when the comet was 277 million miles from Earth. The image revealed something even stranger than the polarization numbers. The glow around 3 Atlas extended toward the Sun, not away from it like normal comet tails. Avi Loeb and Eric Keto analyzed the Hubble data in September 2025. The brightness contours showed a 10:1 aspect ratio, 10 times longer than wide. The sunward glow appeared twice as extended toward the Sun compared to perpendicular or opposite directions. This violates basic physics of solar radiation pressure, which pushes dust particles away from the Sun. How can dust flow toward our star instead of away from it? The geometry of the observation made the discovery even more remarkable. Earth's line of sight to 3 Atlas was misaligned with the Sun-comet line by only 10 degrees on July 21st. We were seeing the extension nearly edge-on, reduced by a geometric factor of 5.76. The actual sunward extension was likely much more dramatic. The sunward antitail combined with extreme negative polarization suggests 3 Atlas carries dust with properties that defy conventional behavior. Particles that interact with solar radiation in ways never observed in our solar system. 3. Atlas originated from the direction of Sagittarius, the galactic center region. It has traveled through interstellar space for millions or billions of years before entering our solar system in 2025. Its retrograde orbit aligns with the ecliptic plane to within 5 degrees, a chance probability of 1 in 500 according to Loeb's analysis. The comet will reach perihelion, closest approach to the Sun, on October 29, 2025, at 1.36 astronomical units, just inside Mars orbit, moving at 68 kilometers per second at maximum speed. It poses no threat to Earth, remaining 1.8 astronomical units away at closest approach, but time is running out for observations. 3. Atlas will exit the solar system forever after its brief encounter with our Sun. The scientific community has mobilized an unprecedented observational campaign. NASA assets including Hubble, Webb, TESS, Swift, Spherix, Perseverance Mars rover, Mars Reconnaissance Orbiter, Curiosity rover, Europa Clipper, JUICE, Lucy, Psyche, Parker Solar Probe, Punch, and ESA's SOHO are all targeting the interstellar visitor. The Mars Reconnaissance Orbiter's HiRISE camera will attempt high-resolution imaging when 3 Atlas passes 30 million kilometers from Mars on October 3, 2025. This represents the closest any spacecraft will come to the interstellar object during its passage through our solar system. Ground-based observatories worldwide continue tracking. The Vera Rubin Observatory serendipitously imaged 3I Atlas during science validation observations from June 21st to July 3rd, 2025, showing gradual coma development before the official discovery. Recent observations show 3I Atlas changing color from reddish to green. Gerald Raymond and Michael Yeager photographed a blue-green gas coma measuring 2.5 arc minutes across on September 7th, 2025. The color shift indicates rapid cyanide production as the comet approaches the Sun. Cyanide molecules fluoresce green under solar radiation. The outgassing scales with heliocentric distance to the 9th power, meaning small changes in solar proximity trigger massive increases in gas production. This steep relationship suggests volatile materials concentrated near the surface, unlike typical solar system comets with more gradual sublimation rates. But the polarization signature remains 3I Atlas's defining characteristic, the measurement that places it in a category by itself among all known celestial objects. No asteroid shows this combination of deep negative polarization and low inversion angle. No comet approaches these numbers, even the previous interstellar visitor. 2I Borisov displayed conventional positive polarization that distinguished it from most solar system comets, but remained within known ranges. 3I Atlas represents something unprecedented, a distinct type of comet that expands the diversity of known interstellar bodies. Its polarization curve suggests grain structures, compositions, and formation environments completely absent from our solar system's inventory. The implications extend beyond a single object. If 3I Atlas carries dust signatures from its birth star system, polarimetric measurements provide a new tool for probing conditions around distant stars, different stellar environments, metallicity, radiation fields. Temperature histories should produce characteristic dust properties detectable through polarization curves. Future interstellar visitors might reveal a library of stellar conditions encoded in their dust signatures, each polarization measurement a fingerprint of alien worlds. But questions remain. How common are objects like 3I Atlas? Are we seeing a rare representative of a vast population or true outlier even among interstellar bodies? The answer depends on detection rates as survey technology improves. The Vera Rubin Observatory, beginning full operations in 2026, will discover hundreds of interstellar objects per year. Each will receive polarimetric follow-up. Statistical patterns will emerge. We will map the diversity of dust properties across the galaxy. 3I Atlas provides the first clear evidence that conditions in other star systems produce materials with optical properties never replicated in our solar system. Its extreme negative polarization and low inversion angle represent a previously unknown category of matter, dust grains shaped by environments we have never experienced. The discovery fundamentally changes how we view interstellar space, no longer empty void between stars, but a library of formation histories written in dust signatures that date back billions of years. 3I Atlas carries the memory of its birth star system, preserved in grain structures that survived the journey across light years and eons. As the interstellar comet approaches perihelion in late October 2025, coordinated observations will refine measurements of its nucleus size, rotation period, and compositional details. But the polarization curve, the first definitive proof of its alien nature, will remain its most significant contribution to science. The numbers tell the story. Negative 2.77% polarization at 6.41 degrees phase angle. Inversion angle of 17.05 degrees. Measurements obtained between July 17th and August 28th, 2025, DART, using 3 different instruments at major observatories across 2 continents. 18 separate observations, confirming the anomaly. Statistical significance beyond doubt. These are the facts that establish 3I Atlas as the most polarimetrically anomalous object ever recorded. The first clear evidence that dust from other star systems carries signatures impossible to reproduce with materials available in our cosmic neighborhood. The Hubble Space Telescope image from July 21st, 2025, Astronomy, revealed another unprecedented feature, a coma elongated 10 to 1 toward the Sun rather than away from it. Combined with the extreme polarization, this sunward extension suggests dust behavior that violates conventional understanding of how particles interact with solar radiation. Advanced computer models will attempt to reproduce these observations. Grain aggregates with different porosities, ice mantles with varying compositions, particle size distributions, unlike anything in the solar system. The modeling will constrain formation conditions in the original star system, temperature, pressure, radiation fields, chemical abundances, but the experimental signature remains irreducible, negative polarization deeper than any solar system object, inversion angle lower than any known comet, dust properties that point unambiguously to alien origin. 3. I-Atlas will disappear into interstellar space by early 2026, never to return. Its hyperbolic trajectory carries it away from the Sun at 58 kilometers per second excess velocity, twice the speed of Oumuamua, nearly double the pace of Borisov. Within decades, it will be too faint for even the most powerful telescopes to detect. But its polarization curve will endure as a benchmark, the first quantitative proof that materials from other star systems exhibit optical properties absent from our solar system, the measurement that opened a new field, interstellar dust archaeology. Future surveys will discover more. 3 I-Atlas analogs, each polarization curve a fossil record of formation conditions around distant stars. Gradually, we will map the diversity of dust properties across the galaxy, trace the chemical evolution of stellar neighborhoods, identify formation environments that produce the most exotic grain structures. The Vera Rubin Observatory will provide the statistical sample needed to understand how common objects like 3 I-Atlas actually are among interstellar visitors. Current estimates suggest one interstellar object passes through the inner solar system every few years, but most remain undetected due to their faintness and high speeds. Improved detection capabilities will reveal the full population. Polarimetric follow-up will characterize each visitor's dust properties. Within a decade, we may have dozens of interstellar polarization curves spanning a range of stellar environments. But 3, I-Atlas will always hold historical significance as the first. The object that proved interstellar space carries materials with properties impossible to replicate using solar system ingredients. The discovery timeline compressed into mere weeks. Initial detection on July 1st, 2025. Confirmation of interstellar origin by July 2nd. First polarimetric observations on July 17th. Anomalous results confirmed by August 28th. Paper submission on September 5th. Less than 10 weeks from discovery to scientific publication. Extraordinary speed for astronomical research. The international collaboration involved institutions across 4 continents: European Southern Observatory in Germany and Chile, Harvard-Smithsonian Center for Astrophysics in Massachusetts, Bulgarian National Astronomical Observatory, Nordic Optical Telescope Consortium, NASA Jet Propulsion Laboratory, University of Helsinki, University of Edinburgh, Observatory of Paris. 15 co-authors contributed to the polarimetric analysis. Zuri Gray of Queen's University Belfast led the observational campaign. Stefano Bagnulo provided polarimetric expertise. Galen Borisov, discoverer of the previous interstellar comet, contributed comparative analysis. The collaboration represents the global astronomical community's coordinated response to rare discoveries. Similar mobilization occurred for Oumuamua in 2017 and Borisov in 2019. But 3 I-Atlas generated unprecedented observational intensity due to its extreme anomalies and the scientific community's growing sophistication in interstellar object characterization. The polarimetric measurements required precise calibration and multiple observation nights to confirm the anomaly. Atmospheric conditions, instrumental systematics, and contamination from background stars all threatened data quality. The team's decision to use small apertures, roughly 2,000 kilometers radius, proved crucial for avoiding stellar contamination in the dense galactic center star fields where 3 I-Atlas was discovered. Each observation night added statistical weight to the extreme polarization signature. By August 28th, 18 separate measurements confirmed the unprecedented depth and narrow width of the negative polarization branch. No instrument error, no systematic effect could explain the consistent anomaly across multiple telescopes and observation nights. The result stands as the most rigorously documented polarimetric anomaly in the astronomical literature. 3. I-Atlas definitively carries dust with optical properties never seen in solar system materials. Its legacy extends beyond a single discovery. The object established polarimetry as an essential tool for characterizing interstellar visitors. Future interstellar objects will receive immediate polarimetric follow-up to search for similar anomalies. The European Space Agency has proposed an interstellar object interceptor mission, a spacecraft on standby to rapidly redirect toward newly discovered visitors. Polarimetric instruments would be included in the payload to measure dust properties during close approach. Such missions could sample interstellar dust directly, returning grains for laboratory analysis. The polarimetric signatures measured from Earth would guide sample selection, targeting the most anomalous materials for detailed study. But even without sample return, polarimetry provides a powerful remote sensing tool for probing dust properties across interstellar distances. Each measurement adds to our understanding of formation conditions around distant stars. 3. I-Atlas opened this new frontier. Its extreme negative polarization and low inversion angle represent a previously unknown category of cosmic dust, materials shaped by stellar environments we have never directly observed. The discovery fundamentally changes our perspective on the contents of interstellar space. No longer empty void between stars, but a repository of formation histories encoded in dust signatures that preserve conditions from billions of years ago and light years away. As 3. I-Atlas continues its journey toward perihelion and eventual exit from the solar system. Its polarization curve remains its most significant scientific contribution. The measurement that proved interstellar visitors carry materials impossible to replicate using only solar system ingredients. The numbers define its legacy. Negative 2.77% polarization. Inversion angle of 17.05 degrees. The first quantitative evidence that dust from other star systems exhibits optical properties absent from our cosmic neighborhood. These measurements, obtained between July and August 2025 using the world's most powerful telescopes, establish 3 I-Atlas as the most anomalous celestial object ever recorded. The interstellar visitor that rewrote the textbook on how dust behaves in the universe. But on October 3rd, 2025 ice. When 3 I-Atlas makes its closest approach to Mars at 30 million kilometers distance, the high-rise camera aboard NASA's Mars Reconnaissance Orbiter will capture the highest resolution images ever obtained of an interstellar object. Those pictures may finally reveal the source of its unprecedented polarization signature, the alien dust grains that carry optical fingerprints of a star system unlike our own.